This video is for the first section of Chapter 6. We're going to learn how to solve systems of equations by graphing. So we're going to be using our graphing skills that we've used the past couple chapters to find the intersection point between two graphs or lines. Our goals are we can solve the systems by graphing and we can analyze special systems. So let's talk about what a system of linear equations is. It literally is two or more linear equations. So in the past we've worked with one equation, now we're going to bring two or more into play. Now a solution of a system of linear equations is any ordered pair that makes all of the equations in the system true, aka the intersection point. So I'd like you to write that. The intersection point of the lines obviously is going to work for both equations because that is the point that they have in common. Alright, our first solving method, we're going to graph each equation and find the intersection point if it exists. So first of all, let's graph these equations in the same coordinate plane. And I'm going to use two different colors so that we can tell the difference between the two. So the first one, y equals x plus 2, I'm going to do in red. And the slope is 1, the number in front, and the b is 2. So let's put our point at the 2 and go up 1 over 1 and connect. And then for our other equation, I'm going to do it in blue, if it'll let me. The m is 3 and the b is negative 2, so first plot the y-intercept, and then go up 3 over 1, using our slope skills from last chapter. And connect with some arrows at the end. Hopefully it's obvious to you that the point where they cross is this intersection point right there, and the coordinates are 2, 4. Now that is the solution of the system of equations. I'd like to show you the checking process, and I'd like you to write this down. The way that you check is you plug in 2, 4 for both equations to make sure that they work. So let's do that now. I'm doing the second equation first because I'm using blue right now. So 4 equals 6 minus 2. 4 equals 4. That works. So the second equation works. And let's check the first one. 4 is going in for the y. 2 for the x. And that also works. 4 equals 4. So we showed how to graph two lines, and their intersection point is called the solution, and then the checking process is just the normal plugging in. Okay, here is a real-life application problem for all you alligators out there, alligator lovers, I mean. This problem is saying scientists studied the weights of two alligators over a period of 12 months. The initial weight and growth rate of each alligator are shown below. After how many months did the alligators weigh the same amount? So first of all, let's define our variables. We have the alligator's weight and the time in months. So let's talk about, let's use T for time in months, and W is the weight of alligators. Now in order to get the alligator's weight, what you're going to do, actually we're going to take a look at the picture on the side. The initial weight is 4 pounds for the first one, and it grows 1.5 pounds per month. And alligator 2 has an initial weight of 6 pounds and grows 1 pound per month. So you can see alligator 1 starts a little bit lighter, but it grows faster, whereas alligator 2 starts a little bit heavier, but grows slower. So we're trying to figure out when did they have the exact same weight. So let's talk about this. Alligator weight is determined by adding the initial weight to the weight that they're gaining per month. So I'm going to do a little organizational chart and then we'll make the equation below. growth rate times the time in months. Okay, alligator 1. Now we're going to make the equations. Alligator 1 initially weighs 4 pounds, and we're adding to that 1.5 t. Alligator 2, initial weight of 6 pounds and gains 1 pound per month. So there's our two equations, and now we're going to plot those. The first equation has a slope of 1.5, also known as 3 over 2, if that helps you, rise over run, and the b is 4, whereas alligator 2 has a slope of 1, which is nice and easy, 1 over 1, and the b is 6. So let's plot those. I'm going to do alligator 1 in red and alligator 2 in blue. So alligator 1 starts at 4 and goes up 1.5, or you can go up 3 over 2. And we should probably extend that a little bit more. Let's see. And now let's do alligator 2 in blue, starting at 6, going up 1 over 1. Okay, so my graph is a little bit off due to not having a ruler. I apologize for that. But as you can see, the intersection point is at 4, 10. So at 4 months, the alligators both weigh 10 pounds. So make sure you write that conclusion sentence or two that I have just written in the corner. They intersect at the point 4:10, and after 4 months, the alligators both weigh 10 pounds. Okay, now let's talk about special systems of equations. So far we've just taken a look at one point, but sometimes there is more than one point of intersection or none. So we're at the top of the next page, and we have here a system of equations that has at least one solution is called consistent. And there's two types of consistent systems. The first one's called independent. And an independent system happens when you have exactly one solution. So in the previous two examples about the alligators and the two lines above that one, those were both independent, consistent systems because there was only one solution. Now the other kind is called dependent, and that happens when there are infinitely many solutions. So that means every point on both lines is a solution. Now, there's also a system that is inconsistent, and that happens when there's absolutely no solution. So that means that those lines will never cross, aka parallel. So you can write that. Parallel lines. And an example of infinitely many solutions, it must be the same line on top of itself. So an example of that would be, well, let me go back, like this. If there's one line, then it's exactly on the same exact line on top, so infinitely many. And it obviously wants me to go to the next slide, so let's do that. Okay, example 3, part A, what is the solution of each system? Well, the ideal form to graph them is obviously slope-intercept. The first equation is not in slope-intercept, so we're going to use our usual operations to move stuff around. And we're going to add x to the other side. Opposite operation, 2y equals 1x plus 2. Divide by 2 to everything, and you get y equals 1/2 x plus 1. So that's the first equation in slope-intercept form, and you may have realized that that's the exact same as the second equation. So we will see that it's going to be the same line. So intersecting at the 1 on the y-axis, going up 1 over 2, that's the slope. Connect with some arrows at the end. And the equations represent the same line, so that means every point on the line is a solution of both equations. Therefore, there are infinitely many solutions, and the system is consistent and dependent. So let's write that now. Now let's focus on the part B. We have the equations y equals 2x plus 2 and y equals 2x minus 1. The slopes are both 2. So if you can recall from the previous chapter, when two lines have the exact same slope, they are parallel to each other. Now, how many times does a set of parallel lines intersect? The answer is no times. So that means we're going to have no solution. There's absolutely no intersection point. So let's plot these lines. Up 2 over 1 with some arrows, and then starting at -1, up 2 over 1. They're going up at the exact same rate. So these lines are parallel, there is no solution, and the system is inconsistent. So there you have it. That is it for the first section. Please take a look now at the summary, concept summary here. This is really helpful. That's why I'm putting it in your notes. The first option is one solution. That happens when there's only one intersection point. The other option is infinitely many, and that happens when two lines are on top of each other. The lines are the same. And then the last thing is there's no solution because the lines are parallel. Feel free to work on the lesson check now if you feel like you have a grasp on this. Otherwise, you can wait until we do these problems together during class.